Okay, so I will start again, first of all, by reminding you a few things. So I give myself E to be a real even dimensional oriented vector space, and I call GE to be an Euclidean metric. And GE star to be the corresponding metric on E star. And we defined, okay, I will define directly the Clifford algebra of E star. I remind you that this is algebra over R generated by 1 E star in E star, and the commutation relations E star prime plus E star prime E star equal minus 2 E star E prime star in E star. So the important thing to notice is that if I scale the metric GE by a parameter T, then the corresponding dual metric scales by the factor T. And so we do have now a Clifford algebra depending on the parameter T, and where here T appears on this side. Well, in the physics literature, this T is often thought as the Planck constant. So the physicists always think of this T as a very small parameter, but we don't care about this. The important point is that, again, for T equals 0, the Clifford algebra C0 of E star is just exactly the exterior algebra. But there is more to this. There is more to this. So the fact is that, so these are facts, and these are actually elementary facts, that there is a canonical isomorphism of vector spaces, of Z2 graded vector spaces. So there is an isomorphism of Z2 graded, not of algebras, but of Z2 graded vector spaces, which says that the Clifford algebra is canonically isomorphic to the exterior algebra, not as an algebra, but as a vector space. So the isomorphism actually is very simple. What you do is that you take, let's say, E1, E2, En to be an orthonormal basis of E star, and these isomorphisms in the other direction, it maps E star, let's say EI1 wedge, EI2 wedge, EIP, with 1 smaller than I1, smaller than I2, smaller than IP. It maps it to C of EI, okay, maybe I will say it, EI1, EI2, EIP, where now the product is taken in the Clifford algebra. So maybe for clarity, maybe I will write it C of EI1, C of EIP to denote that I view these elements as elements in the Clifford algebra. So in other words, the Clifford algebra, as a vector space, it is the same thing as the exterior algebra, but the only thing is that the product rule changes. So in some sense, the Clifford algebra is a deformation of the algebra lambda of E star as an algebra. So this is fact number 1. And fact number 2, so I have asked repeatedly this, that C of E star tensored with C is a simple algebra. Which means that it is exactly the algebra of endomorphisms of a certain space, which I will call SE, which is this famous space on spinors. So of course spinors are mysterious. I realize I I realize this. So this is an endomorphism, actually, an endomorphism of Z2 graded algebras, in the sense that SE itself splits as S plus plus S minus. Okay, so all this is, I mean, this is not difficult to prove, actually. You just do this for for dimension n equals dimension of E equals 2, and then by tensor product, it's very easy to see this. So the last fact I want to mention is the following: that I can define the map supertrace, which goes from C of E star into C. Well, because, I mean, again, because of this C of E star, at least if I tensor it with C, it is just the endomorphisms of SE. And SE is itself a Z2 graded vector space, right? So this is SE. So you can define the supertrace on the Clifford algebra. Okay, so that means that you take the Clifford algebra, an element of the Clifford algebra, you see it as acting on the spinors, and then you take the supertrace, which is again the trace of tau times something. I don't remind you this. And I will state again a very simple but fundamental fact, which is as follows. So fact, it's a very important fact, okay, and I hope that you can see something now because all these things are wet. So I'm just putting water on the blackboard instead of erasing. So the fact is that among the monomials which I described before, C of EI1, C of EIP, which I described before, which are just these ones, with I1, 1 smaller than I1, smaller than I2, smaller than IP. Okay, these monomials span the Clifford algebra as a vector space, since these ones span the exterior algebra as a vector space. The only monomial whose supertrace is non-zero is exactly given by C of E1, C of E2, C of En. So it is the monomial of maximal length which corresponds in the exterior algebra to E1 wedge E2 wedge En, which is a canonical orientation form. Okay, on an Euclidean vector space, oriented Euclidean vector space, there is just one orientation form of norm 1, and actually the supertrace of this monomial here is given by minus 2i to the power n over 2. Okay, so that's an elementary fact. And so if we transport now this result to the exterior algebra, what we get actually is something which says that the supertrace, when you view it as a map defined on the exterior algebra, it corresponds to what's so-called, as we know it, as Bayesian integral. Okay, so that's connection with Bayesian integration. Okay, so I'm now going back to the proof, to the analytic proof of the Atiyah-Singer index theorem. So this will be a sort of 5 minutes proof. And of course, I mean, the fact that proof is 5 minutes doesn't say that the result is easy, but at least it says that in the state of our knowledge, we can give a very short proof of this result. So let me again take X to be compact, Riemannian, oriented, and spin. Okay, so I have the bundle of spinors, STX equal STX plus STX minus. I give myself EGE nabla E to be a vector bundle, Hermitian vector bundle with connection, unitary connection, and I have the Dirac operator, dx. Well, I will not define it, and I simply remind you the Lichnerovic's formula, which says that the square of the Dirac operator is given by an explicit formula C of EI, C of EJ, tensed with RE of EI, EJ, where Kx is a scalar curvature, delta H is called Buckner Laplacian, and RE is a curvature of nabla E. So, okay, so I call for T positive PT of X and Y to be the smooth kernel for exponential of minus T dx squared over 2. Maybe I will put the factor over 2 here for convenience. I mean, you should not take this too seriously. Instead of T, this is for T positive. Right. So there is a simple remark here that if we replace the metric GTX by GTX over T, if we scale the metric GTX by GTX over T, then the Dirac operator dx scales naturally by the factor square root of T dx. So that, in some sense, that's exactly saying that exponential minus T dx squared over 2, I can write it as exponential minus dx squared T over 2. Right, so this is dxt. So in other words, what we're saying basically is that we are just scaling the metric GTX by the factor 1 over T and seeing what happens when T tends to 0. Now, obviously from a metric point of view, if you have a manifold and you scale the metric, you make the metric very, very big, in the limit from a metric point of view, you get a completely disconnected space. That is a space where all points are at infinite distance from each other. From a physics point of view, what this means is that, that means that the temperature gets extremely small. Okay, so you know that the agitation of atoms is connected with temperature. And if temperature goes to 0, becomes 0, atoms do not move anymore. So that means basically that heat does not propagate anymore. So again, think physically, if you put the metric between yourself, get extremely big, in the end, you cannot communicate anymore with each other. You are at infinite distance. So from a geometric point of view, there is no geometry corresponding to T equals 0. No geometry. Okay, all points become at infinite distance from each other. As a metric space, there is no space corresponding to T equals 0. However, what I showed is that from the algebraic point of view, the situation is completely different, because the Clifford algebra CT of T star X, when T tends to 0, just becomes the exterior algebra. And so the proof of the local index theorem will exactly, in some sense, use this fact that when T tends to 0, in some sense, there is a Clifford algebra which becomes nilpotent. We introduce some nilpotent ring to replace the fact that there is no no distance. So how are we going to do this? So let me remind you that we showed that a priori the supertrace of pt and x has an asymptotic expansion b over minus 2 of x divided by t to the n over 2 plus this, plus b0 of x plus b1 of xt, etc. So the expansion, of course, stops. It's not an exact expansion. It's not an analytic. I mean, the function is not analytic or Laurent. It's not a Laurent series, but it's to any order. And what we're going to show, actually, is that when t tends to 0, actually, when t tends to 0, we're going to show that all these terms disappear, at least until this, and that this b0 of x can be computed explicitly. Okay, so the sort of techniques that we're going to use, actually, I mean, physicists have been extremely helpful in reformulating the problem. I will not say in what sense or in what extent, but the technique I will explain more or less results of this. So first of all, again, an algebraic fact. Algebraic fact. So the first fact is completely elementary. It is the fact that if, again, you give yourself E, GE to be an Euclidean, even dimensional, okay, maybe a vector space, I just say for the moment, then I am saying that lambda of E star is C of E star module. So in other words, the exterior algebra itself is a representation space for the Clifford algebra. Okay, so to describe this, I will just identify for the moment E to E star by the metric. So I will describe what the Clifford action is. So I give myself E in E, and I'm saying I define C of E being E star exterior minus contraction by E. Okay, so what does this mean? So this is a contraction by the vector E. If you have a P form, you can contract it, and you get it by a vector, and you get a P minus 1 form. This is the first term. This term here, so E star is corresponding to E by the metric, by the canonical isomorphism, so it's a one form, and this E star wedge acts by the product, by the one form. So that's the definition. So this is an element of end of lambda of E star. And so it's extremely easy to show that this map actually extends to a representation from C of E into the endomorphisms of lambda of E star. So basically, what you have to check is simply that C of E prime plus C of E prime C of E is equal to minus 2 E prime. And that's an elementary computation. So from a more abstract point of view, since we know that C of E is the same thing as lambda of E star as Z2 graded vector spaces, this action, which I defined on lambda of E star, just corresponds to left multiplication. It just corresponds to left multiplication of C of E on C of E. So in other words, the Clifford algebra acts on itself by left multiplication, and the morphism that I described by an explicit formula on lambda of E star just corresponds to left multiplication on C of E. But now, actually, this is one of many representations, because, I mean, basically, we can always conjugate such C of E. Let's say we can conjugate the C of E by, let's say, S to the power n lambda of E star. So n lambda of E star is just a number operator of the exterior algebra. It acts by multiplication by P on P forms. So basically what I will do is that definition. So I define Ct of E now for T positive. Ct of E is given by, well, there is just, I introduced square root of 2 here. I mean, don't pay too much attention to this square root of 2. E star wedge minus square root of T divided by square root of 2 contraction by E. Sorry?
Please repeat number n.
So n lambda of E star is just a number operator of lambda of E star. So in other words, it acts on differential forms of degree P by multiplication by P. That's a number operator. Okay, so it's a linear operator, and I'm saying simply that this representation of the Clifford algebra, I can always conjugate it by these powers of S to the n lambda of E star, and I get a new representation. Okay, so if you conjugate a representation, you still get another representation. That's very obvious. And so I define a specific conjugation this way, which probably means that I took here S is equal to square root of 2 divided by square root of T. So this still gives me a representation of the Clifford algebra. So in other words, I can define this way a map from A in C of E, and this map, I call it CT. This goes into the endomorphisms of lambda of E star. That's the representation CT. Okay, so what I will try now to do is give a formula for the supertrace. So, in other words, if I take CT, if I take any element B in the end of lambda of E star, okay, so it's extremely easy to show that as an algebra, the endomorphisms of the exterior algebra are spanned by exterior products and contractions. Okay, so in other words, any element of the endomorphism of the exterior algebra can be written in a unique way as a sum of Aij of Ei, or let me write it this way, Ei cross Ej. So where, I mein, Ei is just Ei1 wedge Ei2 wedge Eip, and Eij is just Eig1 Eigq or something. Okay, so you can write uniquely an endomorphism of the exterior algebra this way. That's very easy. So such operators are called annihilation operators. These operators are called in physics as creation operators. Okay, and to get a unique decomposition, you always put the annihilation operators on the right-hand side. This you can always do. This means that in the physics terminology, this is called normal ordering. Okay, so in this, maybe I will write it with a Bij, sorry, with Bij. And so what I'm saying is there is a distinct coefficient here, which is a coefficient of E1 wedge E2 wedge EM. There is this coefficient which I will call for some reason B max. So that's a coefficient in this expansion in which you only have creation operators and you do not have any annihilation operators. There is nothing here, there is just E1 where G2 where Gn. Okay, so in operators like this you can always expand it and you select this B max. And so I'm going to give the simple algebraic fact which follows from what I said before, which is proposition if A lies in the Clifford algebra of E, or of E star, okay, I just identify them now, then the supertrace of C of A is equal to minus I t to the power n over 2 times Ct of A max. Okay, maybe I'll write it this way, supertrace of A, supertrace of A. So this is a supertrace on the spinors. I obtain this supertrace by representing A as Ct of A, expanding the Ct of A in terms of creation and annihilation operators, picking up the term of top degree, and simply scaling it by the factor minus I to the n over 2. So let's see why the proof is completely elementary. Proof. So, first of all, so we know again that C of E, the Clifford algebra, is the same thing as the exterior algebra, as a vector space. So, I gave you the algebraic fact that among the monomials in the EIs, only the top degree monomial has non-zero supertrace. So, which means that if A is equal to just correspond to C of EI1, C of EI2, C of EIP, with P strictly smaller than the dimension, then the supertrace on this side is 0. That's what I said before. But now, on the other side, if you just think what is the Ct of A, you just replace again. Every time you have EI1, you replace it by EI1 minus contraction by E1. And so you see well that when you're doing the products of these, you will never reach the point where you will have a top degree monomial, because you only have P terms where P is strictly smaller than N. So in other words, in this case, this is 0, and this is also 0. So the only interesting case is a case where you can take A to be I1, I2, In. Let's say IE1, E2, etc., En. So in this case, the left-hand side is minus 2 I to the power n over 2. This is the left-hand side. Now, on the right-hand side, well, I mean, if you think of what is the coefficient of, on the right-hand side, the coefficient of E1 where G2 where Gn will be simply square root of 2 divided by square root of t to the power n. It will just be this. Because when you make the product of objects like this from E1 to En, the only top degree term is the one which comes with E1 times E2 times En. So you will get exactly square root of 2 divided by square root of t times this. So indeed, this is the right-hand side when taking this thing max. This, in other words, I'm taking this Ct of A max. It will be exactly this. And so to recover the left-hand side, you have to multiply this by t to the n over 2, and also by minus I to the n over 2. And then you get the right-hand side. And this is what I wrote here. Okay, this is what I just wrote here. That's this identity. That's a completely elementary identity. I mean, if you just think of it. And so it is this fact that we're going to use to overcome the singularity of the heat kernel. Because, okay, so let me just give a purely formal argument. So we know a priori that the supertrace of Pt of x and x, well, it behaves like 1 to the t to the n over 2. We know a priori, by abstract arguments that I explained last time, that there is a singularity like 1 to the t to the n over 2. Now, Pt of x and x, this is actually an element of the Clifford algebra of Tx and x tensored with end of Ex. Because it's an element of the endomorphisms of the spinors at x tensored with E. So it is just obviously an element of these. And now what we will do is that we take this element of the Clifford algebra and we take this precisely, this CT morphism. In other words, every time we have an element in the Clifford algebra, you just transform it, you represent it via the CT. Okay, now we use the fact that, again, Pt of xx is an element of Clifford algebra. We represent it on the Clifford algebra, on the exterior algebra. And so if we do this, we'll have now equal to, this will be equal to minus I to the n over 2 times t to the n over 2 times, okay, maybe I'll just keep the trace in here, and then I will have qt of x and x max, where qt of x and x max is exactly the one that I defined before. Okay, this is just an algebraic trick for the moment. Okay, I've transformed, re-expressed the supertrace by using the CT morphism, and of course this qt has been obtained from Pt by using the CT morphism. So I've mapped the Pt to qt. So you have the t to the n over 2 here. But now again, by abstract arguments, we know that qt of x and x behaves like 1 to the t to the n over 2.
Sorry, what's
qt has been obtained from Pt by applying the CT representation. Okay, Pt, okay, forget about E. Pt is a section of the Clifford algebra. We represent the Clifford algebra as acting on the exterior algebra. Okay, and I'm just using the result I gave before. So in other words, I'm saying that this is equal to this times this. But now qt will have a singularity like 1 to the t to the n over 2. This we know a priori. But now you see that the t over n over 2, they kill each other. They kill each other. So the singularity has disappeared. Okay, so this is the idea behind the proof. Okay, so, I mean, you know, one cannot too much believe in miracles, because obviously what I'm telling you as a proof is a sort of joke, because, I mean, you know, if every time you have a singularity you could just destroy it by using some representation theoretic trick, it would not work. But that's essentially, in some sense, the key ingredient with respect to what was known before is doing this. Okay, so let's see how to do it. How to do it precisely. Okay, so step number 0, replace x by Rn. Okay, so what this means is that the expansion, I mean the behavior of Pt and x as t tends to 0 is local on x. So being local on x, that means that you only need to know the metric and everything near a point x. So it is no obstacle, actually, to replace x by Rn and to assume that we are on Rn. Let's say in a small open set we have a non-trivial metric. On a small, but outside everything is trivial, that is, the metric is flat. It's no problem to do this, actually, from an analytic point of view, just by assuming this, we are on Rn and the point x, that the point x is just equal to 0. Okay, so the point x is just represented by 0. X is equal to 0. Okay, so we're going to do several things. First of all, we trivialize the vector bundles Tx, Stx, and E by parallel transport along, say, radial geodesics. Okay, you could take as well geodesic maps. So we have this radial geodesics, and we identify the vector bundle here to this one by parallel transport. Okay, so by doing this, actually the vector bundles Stx and E have become trivial. So they have been identified with their values at Stx(x) and Ex, or E0 if you like. So in other words, our operators now don't act anymore on sections of the vector bundle, they act on sections of a vector space. Now, the second thing that we do is that we do a change of coordinates. We make y gives y divided, y gives y, okay, let's say divided by square root of t. So in other words, we conjugate, let me call ft of f and y. This is f of square root of ty. We replace the operator, we conjugate the operator this way by a square root of t dx square f1 over square root of t. We just do a trivial conjugation. We do a change of variables on the operator. Okay, so let me call this operator LT. And so this operator LT, we have a new kernel. We call Qt of y prime, the C-infinity kernel of LT. And so it's extremely easy to, of exponential of minus LT, of exponential minus LT. So it's fairly easy to show that Pt of 0 and 0 is equal to 1 over t to the n over 2 Qt of 0 and 0. This just is a trivial application of a change of variable formulas. This is not deep. Now, step number 3. Step number 3. So our operator LT is now a section of what? It's a section of the Clifford algebra of Txx tensored with end of Ex, tensored with scalar up at x. So these are differential operators acting on Txx. So what I'm saying is that the operator LT can actually be viewed now, because we have trivialized the vector the vector bundles, so we're just acting on vector spaces, it can be written as a matrix of differential operators. So this is a matrix part of the operator LT, and this is a sort of scalar differentiation part. And so what we're going to do is make the morphism that I explained before, CT. We make the morphism CT, which means that now I will have here end of lambda of T star XX tensored with end of EX tensored with op on TXX. Okay. That's the last critical step. That's an algebraic step which consists to view the operator as a matrix operator with coefficient in the Clifford algebra and use this representation of the Clifford algebra on the exterior algebra.
The right
Oh, differential operator. That's scalar differential operators. Scalar differential operators. Okay, so in other words, I mean, any differential operator is, of course, acting on a vector space, not a vector bundle, is a matrix of differential operators. Okay, so the matrix part acting on the spinors, I wrote it as Clifford algebra, and now I map the Clifford algebra to the endomorphism via this representation. And now again, I'm going to use this. Okay, so I'm going to use this. I will then say that the supertrace of PT of X and X, so let me call, sorry, I get this way an operator MT, I will get this way an operator MT. So let me call, I looked at exponential minus MT and I call RT of YY prime its kernel.
operators on the fiber over X.
Yes, because, absolutely, because I've now trivialized, okay, the operators, I'm at a point, I've trivialized everything. Okay, so it's not, it's just the fibers have been come back to just a single vector space, so that I can now view the operator as acting not a section of a bundle, but a section of a vector space. Okay, so it becomes... It's strange because
you've got derivatives over a base, not over a fiber.
Yes, yes. So that's why, you know, I extended everything to Rn to allow these.
I see.
Okay. So ultimately, if I put everything together, when taking the supertrace, I will get supertrace of PT of X and X. I use what I said before. This will be minus I to the n over 2 trace over E of RT of 0 and 0 max. Okay, so I used the algebraic formula I said before. The algebraic formula I said before meant that exactly if I use the CT representation, there is a T to the n over 2 which is going to kill the other one. Okay. And now what we have to look at is to see what happens to the operator T dx squared over 2. I just rewrite it as minus delta HT over 2 plus T kx over 8 plus T over 4, CT of EI, CT of EJ. Sorry, I'm going to write directly here, empty. Well, no, sorry, I write for the moment T dx squared over 2. I just leave it this way. So I have here C of EI, C of EJ, tensored with RE of EI, EJ. So let's see what happens when t tends to 0 on this object. Okay, so I take this object, but of course I do at the same time the change of coordinates on one hand and the transformation of the Clifford algebra on the other hand. So let's look at the simplest term. This one here, ultimately, the scalar curvature will be evaluated at square root of ty. Okay, so again, I have this coordinate centered at x, here is y, I just scale y by the factor of t. So when t tends to 0, this disappears. This is by far the easiest term. Now, on this one I have to put here Ct of E, Ct of Ej, and here are at square root of ty. And now you see that the Ct of E has exactly a singularity which is 1 over square root of t. The singularity of Ct of E is 1 over square root of t. This is the formula I gave. So that ultimately what you find is that this term here converges to, as t tends to 0, to 1/2 of Ei wedge Ej tensor with Rex of Ei Ej. Okay, in the Ct you had this singularity 1 over square root of t. So when t tends to 0, only these singular terms survive, and they are factors of Ei and Ej. And so you get just this. Okay? And this you recognize here, the curvature tensor as a form. Okay, so the most difficult term is this one. So let's try to understand this term. Okay, so we're going to use the fact, elementary from the point of view of differential geometry, that if you have a vector bundle with connection, nabla f, and if you trivialize the vector bundle by parallel transport, so you trivialize f by parallel transport along, let's say along geodesics, but they could be actually along any radial lines, it doesn't matter, using the connection nabla f. So you do this trivialization, which means that the vector bundle is trivial. So f has been identified with fx. And so the connection nabla f can be written in this trivialization as d plus gamma. Okay, the connection on a trivial vector bundle can always be written as d plus gamma, and gamma is just a connection form. And so what I'm saying is that the connection form as an expansion. Okay, so gamma at y. So in other words, here the point y now, in the tangent bundle, okay, I just take gamma evaluated at y, that's a connection form, is given by 1/2 of the curvature at x of y plus O of y squared. Okay, that's the expression of the connection form. The connection form, once you trivialize the vector bundle by parallel transport using the connection nabla f. Okay, and RF, sorry, this is RF. This is the curvature of nabla f. This is an extremely easy result. Okay, so let's apply this to the tangent bundle. So let's apply these to the tangent bundle. So we take f equals cx. So maybe I take gamma f here to be clearer. So gamma tx will be equal to 1/2 of rtx of y at x plus O of y squared. But now I claim that I can, from this formula, obtain a corresponding formula for gamma STX. Okay, so this I do not completely explain. This is related to the question of the spin representation that I see that many of you like very much, or at least would like to know more about. So let me just say that gamma of STX, there is an exact formula which says that this is equal to gamma TX of EI of, let's say, EK-EL times C of EK C of EL. Okay, here gamma TX takes values in antisymmetric matrices, right? Because the connection on TX preserves the metric, so the connection form has to take values in antisymmetric matrices. Okay, so I'm saying that there is this formula. And so basically using this, you find that gamma STX at y is equivalent to 1/2 of gamma of RTX of y and something EK-EL C of EK C of EL. Okay, so the operator T delta H over 2, it's essentially the sum of T times the sum. Okay, I forget now completely about the vector bundle E. I forget about E. This is too simple, okay? I will just make E equals C. So we forget completely about E. So this is just equal plus gamma of STX of EI squared. That's the definition, that the sum of the covariant derivatives on a spinor is to the square. And so this is just equal to delta plus nabla EI. I just use the formula which is there. This is falling apart, so. Okay, so I will use the fact that I scale the operator, so I use a conjugation here, and I take here at square root of ty, because this is the effect of the conjugation we took. So the nabla of EI gets scaled by 1 over square root of t because of the change of coordinates, and also the gamma is evaluated at square root of ty. So I do have this divided still by square root of t, and here now I will replace this by the formula which is up there, plus 1/8 of RTX at x at square root of ty and EI, EK, EL, C of EK, C of EL squared. And then, of course, there is an O of ty squared that I will not bother about. I'm doing the expansion this way. But of course, since I replace the C by the CTs, I have also to do this. Okay, so what I've been describing now is the effect at the same time of the change of variables plus the transformation on the Clifford algebra. And now, what you see is the following thing. that we're going to put the t inside. So the t inside means that I just scale here by the factor square root of t, and I just scale here by the factor square root of t here. But now again, you see that this gives a power t here. There is a power t, and the ct themselves have a singularity which is 1 over square root of t. So that ultimately what you find is that when making t tend to 0, after doing the proper change of coordinates and change of the Clifford algebra, this converges to, I do not give the detail of the computation, converges to minus 1/2 of nabla EI plus, 1/4 of RTX Y EI EJ, EKEL EK wedge EL square plus REX. That's all what survives from the operator after change of coordinates and using the representation of the Clifford algebra. But now we use the 2-by-2 symmetry of the Levi-Civita curvature. The 2-by-2 symmetry means that these two arguments here can be exchanged. And so we write this as minus 1/2 of nabla EI plus 1/2 of RTX Y EI square plus REX. Okay, where RTX is of course viewed as a two-fold. So this is the limit in the proper sense. After using the rescaling of coordinates plus the representation of the Clifford algebra, this operator has a limit which is non-trivial. It's this one. And now, elementary analytic arguments say that we can effectively, at the level of the kernels, pass to the limit. So we can pass to the limit. So what this means is that in some sense it is true that RT of 0 and 0 converges to, as t tends to 0, to R0 of 0 and 0, where R0 is a heat kernel for this operator. So R0 of YY prime is just the heat kernel for this exponential of M0 minus M0. And so what we just have to compute, is minus I to the n over 2 trace over E of R of 0, 0 max. This is what's left to compute. So we already see that the supertrace is non-singular, as t tends to 0, and we're left to compute this. But actually, when taking the exponential of this thing, we have actually the exponential is the product of two exponentials. In particular, we see appear the exponential of minus the curvature. Because when you take the exponential of this, the exponential of the curvature gets out. And so when taking the trace in E, you have the trace of the exponential of minus the curvature. And so what's left is a computation of the kernel for this heat kernel for this operator. Okay, but this is well known by physics result, is a heat kernel for a harmonic oscillator-like operator. And if you do the computation, you find that this R of 0, 0 actually is given by this exactly times the A roof of RTX. In other words, if you compute the heat operator for this operator, which is rather simple, it's an operator acting now in a vector space. You compute its heat kernel. There is an explicit formula called the Meller formula. You compute the heat kernel on 0 on the diagonal, and you get the A roof of RTX divided by 2 pi to the n over 2. And so you have to combine this with 1i to the n over 2. You have to take this thing max. And this proves the local index theorem, which I reformulate as saying as t tends to 0, sorry, I think it's back here. So theorem as t tends to 0, supertrace of pt of x and x converges to the form A roof of Tx, nabla Tx, Ch of E, nabla E, max. Okay, and as I explained before, it implies, of course, the index formula. So, just a hint of history. The proof of this result, as I outlined it, follows the method indicated by Getzler. But the first proofs came from not using this method, and Etienne-Bott-Petodi. I would say Petodi first for the case of the theorem complex, then Gilkey and Etienne-Bott-Petodi, and this is the proof I outlined before, which was devised under the influence of mathematical physics. So, as a remark here, there is an interpretation of the proof which follows apparently a completely different sort of thing, but which is very much connected with mathematical physics, using supersymmetry and which says basically that you can interpret the supertrace of exponential minus t dx squared over 2 as the integral over the loop space of the manifold X of a certain form which I will call gamma t, which is actually closed with respect, it's not with the classical theorem theory, but with respect to equivariant cohomology. For the equivariant cohomology of Lx with respect to the action of S1 on Lx, so the loop space of the manifold is acted upon by S1, and X appears in Lx as a fixed point set of this action. Okay, you have a loop, you can rotate it, right? And obviously the loops which are fixed in the rotation are just the points. And that the index formula, at least formally, appears as a consequence of a localization principle, which says a certain integrals localized by a residue formula on the manifold X directly by algebraic arguments, and then you get the index theorem. Okay, so I also explained that from the Laplacian index theorem you get the Riemann-Roch-Hirzebruch formula. So if X is a compact, and compact, and if E is a holomorphic vector bundle on X, you can define its Euler characteristic with coefficients in E, which is the alternate sum, the dimension of the cohomology groups, let's say of the sheaf theoretic cohomology groups or the Dolbeault cohomology groups. And using what I said before, you get the formula of Riemann-Roch-Hirzebruch, which says that this Euler characteristic is given by the integral over X of Todd of the holomorphic tangent bundle paired with a Chern character of E. And so the proof is as follows. If, let's say, X is scalar and the metric is scalar, you take a Cayley metric, then the operator dx is actually, if I take square root of 2 d bar x plus d bar x star, this is a Dirac operator in the sense I gave. That's a classical Dirac operator. That's very easy to show. And so it's easy to see that the index of dx plus using Hodge theory is just the Euler characteristic. So in general, in this case, you can see that the index of dx plus is precisely the Euler characteristic. You apply a Thiers-Singer, and then you get Hirzebruch formula. If the manifold is non-Kähler, well, you can still use the Thiers-Singer index formula, because even though dx is not equal to d bar x plus d bar x star, so these operators are no longer equal, but they have the same symbol. They have the same principal symbol, and since the index is a homotopy invariant, you can use a Thiers-Singer index theorem. Again. So, what have been the applications of the local index theorem? Up to a certain point, it was just used to prove the index theorem. That was, of course, one of its main applications, to prove the index theorem. And I mean, what I mean by use the local index theorem, the fact that we have a local in the sense that the supertrace is non-singular, which is in some sense a fact which is independent of the index theory, but of course which allows you to prove the index theorem. But in terms of application, it was used in two ways, just to prove the index theorem, and also to prove the index theorem for manifolds with boundary, So I will not cover this at all. And we will now move to the families index theorem. Okay, so families index theorem. So this is a relative form. It's a relative form of index theory. So what means a relative form? Which means I give myself pi to be a projection, a summation of manifolds. So pi is a summation with compact fiber So it's a proper map. It's a compact fiber Tx, and we assume that Tx to be oriented, even dimensional, and spin. So we also give ourselves again a vector bundle E-G-E nabla E on M. And so in this case, if you give yourself GTX to be a metric, so Tx here is just a relative tangent bundle. It's Tm over S. It's a relative tangent bundle. It's a tangent bundle to the fibers. So I give myself GTX to be a metric on Tx. So I claim that from these data, you can build the operators dxs. So dxs is the Dirac operator along the fiber xs, so it acts on sin infinity of xs with coefficients in stx cross E, restricted to the fiber xs. So in each fiber, you have a Dirac operator. In each fiber, you have the Dirac operator. So let me look at the kernel of dxs. So for simplicity, I will assume that kernel of dxs has locally constant dimension. That's an assumption. Okay, so what we know is that the index of dx plus is constant, is locally constant. This is for sure because the index is a homotopy invariant. But I assume that in some sense, I will assume assumption for simplicity that the kernel of dxs doesn't jump, which means that the kernel of dx plus and the kernel of dx minus have themselves constant dimension, not only the difference. You can always go back to that situation. So, in this case, you can define the so-called index bundle. You can define the index bundle definition. The index bundle, index of dx, that's by definition the formal difference of the kernel of dx plus minus the kernel of dx minus. Okay, this is a difference which is taken in the sense of K-theory. If you don't know what K-theory is, you just think of vector bundles, and instead of taking the sum, you take the difference. I mean, difference in this case is just purely formal. I mean, just by using a Grothendieck sort of game to define a category with, you just can construct this sort of thing. And this is a so-called index bundle. When this assumption of local constant dimension is not verified, you can always deform in a certain way to this situation. So, what is the family's index problem? Problem is to compute the index bundle of dx as a bundle in K0 of the base. We want to compute this bundle as a bundle on K0 of S, and more specifically, what we want to find is its Chern character. We want to find the formula for the Chern character of this index bundle. We want to get a formula for the index bundle, for the Chern character of the index bundle. So let me just state the formula of Atiyah and Singer for the Chern character. So theorem, the Chern character of the index bundle of dx is equal to, so this is pi star. Pi star is integral along the fiber of the A roof of Tx paired with a trend character of E. So it is again, so this is an identity in H even of S with coefficients in Q. So remark, if S is a point, this formula is just the ATS single index formula we just proved. This is the index formula, classical index formula. Now, what we will show is how to prove a refined form of this identity. So, in which now really the local character of the index formula will be used. So in other words, the idea will be to replace cohomology classes by differential forms. So in other words, you can, if you have connections on all the vector bundles involved, Tx, nabla x, E, nabla E, you can represent the right-hand side by differential forms, the left-hand side by differential form, and then you can ask yourself whether these differential forms are equal. And so this is what we're going to do, and this will use superconnections. But before doing this, I will show to you that you already met superconnections and that you already used them, that as we say, maybe that you did use superconnections without knowing it. Just to paraphrase Le Bourgeois gentilhomme, that he was doing prose sans le savoir, he was doing prose without knowing it. That's a famous play by Molière, so you were probably doing superconnections without knowing it. So let me take again, first of all, the theorem complex, omega m dm. I just considered the theorem complex. So we leave the Dirac operator problem for the moment, that the theorem complex of M. So dm is an operator, is an odd operator whose square is equal to 0. And so what we're going to do is the following. We are going to introduce THM, which is a horizontal vector bundle. So in other words, we introduce a splitting of Tm equals THM plus Tx. You can always do this. You can pick, for instance, a metric and define THM to be the orthogonal bundle to Tx. It's very easy. So we can always do this. So once we have this, so this is actually equal, there is to pi star of Ts plus Tx. Because THM is obviously identified by projection to the pi star of Ts. So using this, we can give the identification. This is just equal to the pullback, the exterior algebra of the total space is the tensor product of the exterior algebra of the base, graded tensor with the exterior algebra of the fiber. Right, of course, this is a non-canonical identification in the sense that it depends on the choice of THM. So because of this, we can write smooth forms on M. Smooth forms on M can be thought of as smooth forms on S with coefficients in smooth forms on X. I mean, I was just writing actually a differential form on M as a product, sum of products of form on S times forms on X. So this allows me actually to write a form on M as being a form on S with coefficients in forms on X. This is an identification of Z-graded vector spaces. The grading here is a total grading. Now, it's fairly obvious that omega M is a omega S module. I mean, in other words, if you take a form on M, you can always multiply smooth forms on M by pullbacks of forms on S. And of course, since the theorem operator verifies Leibniz rule, then the operator dm verifies Leibniz rule with respect to multiplication by omega of S. Since it verifies Leibniz rule on M, it obviously verifies Leibniz rule by multiplication when you just restrict multiplication by multiplication on S. Now we use this identification here. So using the identification star, so in effect what we discover is that dm is a superconnection on the Z2 graded vector bundle omega x. So omega x now, the theorem complex, the relative theorem complex, is a vector bundle on the base. It's a Z graded, then it is Z2 graded, so it's related to gram. Okay, so if you put everything together, so dm, because actually dm is odd, it maps even forms into odd forms, so, and odd forms into even forms, so it is odd, and it verifies Leibniz rule with respect to multiplication by S. So dm actually is a superconnection on omega of x, and what is its curvature? Its curvature, since dm square is equal to 0, its curvature is 0. So not only have we already met superconnections, but we've met actually flat superconnections. So how can we view actually dm as a superconnection? So now we're going to force ourselves to view dm as a superconnection. I told you that there is a general structure of superconnections, and then a superconnection AE is always given by nabla E plus B, where B lies in something odd, in certain odd algebra. So I will now force myself to write the operator dm as a superconnection this way. So first of all, a connection. We're going to construct a connection on omega x. So the relative theorem complex, we're going to put a connection now on it. A connection is viewed as a vector bundle on the base. So definition. If U lies in TS and S lies in omega of x, so I should say a section of omega of x, it's a smooth section on the base of omega of x. By definition, nabla U omega x. So I'm computing. So I give the formula. This will be given by the Lie derivative, LUHS. So let's try to understand this formula. So to understand this formula, I say that UH is the lift in THM of U. So if you vector TS, you can lift it to UH. So it's your unique lift. So this is a Lie derivative operator. And it's an elementary fact to check that the Lie derivative operator with respect to UH acts on such S in a tensorial way. That is, it's in effect tensorial. I mean, in the sense that if you multiply U by a function, you get just, contrary to what it seems. Usually Lie derivatives are not tensorial, but in this case, they are. So this defines a connection on this relative de Rham complex. Now, a second fundamental object is this following object, definition. If U and V lie in TS, by definition, TH of U and V is equal to minus the projection on TX of the Lie bracket UH VH. So in other words, you take two vectors on the base, you lift them horizontally, you take the Lie brackets, and you project on Tx. So this is a projector on Tx with respect to the splitting Tm equal Thm plus Tx. This is again a tensor. It's very easy to verify that it is a tensor with respect to U and V. So in other words, TH is a section of lambda 2 of T star S P star tensored with Tx. It's a two form with values in Tx. And I claim proposition that we have the following formula. The de Rham operator, dm, that's our initial de Rham operator, poor de Rham operator, we can exactly split as a sum of three terms. There is the first term is nabla omega x. The second term is a de Rham operator along the fiber. And the third term is a contraction by th. Okay. So let's try to understand this. So this is a full de Rham operator. I told you that there is a structure theorem saying that any superconnection splits as a sum of a connection, a classical connection, plus an odd object in the algebra, actually in this case, in this algebra, lambda of T star S tensored with end of omega of x. So it has to be a section of this odd piece. So why is that? Because, okay, so this formula is very easy to prove. That's an easy formula to prove, but let's see that this in effect has a preferred structure, because in effect dx is an endomorphism of the relative de Rham complex, which is odd. Obviously it's odd. It exchanges even odd forms. And ITH, what does this mean? That means that we view TH as a two form on the base, and we contract any form on X by TH. So it means that this ITH decreases the vertical degree by 1 and increases the horizontal degree by 2. It decreases vertical degree by 1 and increases horizontal degree by 2, so that in effect it is globally odd. because as a contraction operator it is odd by 1, and as a form it is even. So globally it is odd. And the proof of this formula is elementary. So let me insist on the fact that this superconnection is not simply the sum of a connection and an odd operator. Basically, that was the only example that we had, connections and odd operators. And now we have a third thing, which is a funny object, which actually plays a fundamental role when understanding the Laurent spectral sequence of vibration, this ITH, which is responsible actually for when we compute Laurent spectral sequence. And actually, when we're going to prove the family's index theorem using superconnections, we will have to keep in mind that the natural objects which appear as superconnections are not simple-minded as superconnections. They are more involved than that. Okay, I think that I have to stop here. Is it correct? It's 1? Yeah, okay, thank you.